Okay, so we got a work problem. All right, work is the it takes a certain amount of work to get something done. So on these work problems, you're always going to have two items working alone, okay, and one item working, and then a situation where both of them are working together. Okay, so it might be, hey, I've got two different hoses to fill the swimming pool. Okay, like on this one, it takes one hose this much time, the other hose this much time working alone. How long does it take working together? Or we've got a theater with two doors to get everybody out in case of a fire. Door number one working alone is 2 minutes to get everybody out. Door number two is 5 minutes to get everybody out. How long would it take to get them all out together? You know, something like that. So on this one, it's a little different than that, but not significantly. And it says it takes a smaller hose 4 times as long to fill a small swimming pool as it does a larger hose. Okay. And it takes 20 minutes for them working together. Now, this is the setup that you always get for free on these problems. You get 1 over something plus 1 over something equals 1 over something. Now, these two somethings on the same side of the equation, those represent the two hoses working alone. And then over here, where it's just one fraction on the other side of the equation, that represents them working together. So it's 20 minutes working together. Now, it doesn't say how long either of the other two are working alone, but we do know that the smaller hose is being compared to the larger hose. So let's make X is the larger hose. A larger hose can be on the left fraction or the right, it doesn't matter. Okay, and so over here, we already took care of the larger hose, so the smaller hose is going to be the same amount of time multiplied by 4. And now we've got, what we need. So now it's time to multiply both sides of the equation by the least common denominator, which is going to be 20x. Okay, so when we go x times 20x, the x's cancel, and we get 1 times 20, which is 20. Then when we do 20x times 1 over 4x, the x's will cancel, we'll cancel a 4, and we'll get 5 times 1. Or 5. And then here we'll get cancel the 20s, and we'll just get 1 times x. And x, that worked out pretty good, is 25. So the slower hose is a 25-minute hose working alone. No, I'm sorry, that's the faster hose. Yeah, because we said, hey, the larger hose, the faster hose, that's going to be our x. Okay. So what about the slower hose, the smaller hose? Well, that's going to be 4 times x. 4 times 25, so that's going to be a 100-minute hose. So we got a 25-minute hose and a 100-minute hose working together. They get it done in 20 minutes. In 20 minutes. So if the faster hose works alone, it's not much of a difference because the slower hose is really slow. But that's kind of how these work problems go. Okay, so now we're going to do distance, rate, time problems. Okay, this looks like a job for dirt because distance equals rate times time. Okay, so let's start organizing information here. Okay, so we got distance, rate, time. Okay, and on these problems, we usually have 2 scenarios. In this case, one scenario is, let's see, a rowing team rowed 60 miles while going with the current. So with the current is one scenario. I guess I don't need the W. And against the current, that's going to be the other scenario. All right, so let's fill out what we can here. So 60 miles while going with the current. So our distance with the current is 60 miles. And against the current, they go 30 miles. Incidentally, I'm making this video during the Olympics of the 2020 Olympics in 2021. And I have seen some rowing, and it's pretty cool. Okay, now it also talks about the rate. Okay, and it says the rate of the current was 3 miles per hour. Okay, and we're looking for the rate of the rowing team in still water. So how fast can they paddle if the water isn't speeding them up or slowing them down? So whatever we're looking for, we'll call that x. All right, so the rate with the current is going to be how fast they're able to go plus another 3 miles an hour. But when they're going against the current, their speed will be their normal speed reduced by 3 miles an hour. Okay, cool. Now, what about the times? They don't say much about the times, but they do say same amount of time. Well, let's take our dirt formula and solve for t. If we divide by r on both sides of the equation, we get t. And we find that time is going to be your distance divided by your rate. So if we take our distance divided by our rate, the time for the first one will be 60 over x plus 3. And the time for the second voyage against the current would be 30 over x minus 3. But again, it says same amount of time. Therefore, we know that the time with the current and the time against the current are the same thing. Now we have an equation where we can solve for x, and x is what we want, the rate of the rowing team in still water when there's no water going, or no current going on. So we've got a fraction equal to fraction. That's called a proportion. So let's just cross multiply and get 60 times x minus 3 times 30 times x plus 3. And of course, we should get rid of those parentheses so we can access the, whatever they're called, the variables. And let's see. Okay, so let's subtract 30x from both sides. And then we'll add 180 to both sides. And then we'll divide both sides by 30. 27 divided by 3. What is that, like 9 or something? Okay, and 9 miles per hour. That's how fast they go when there's no current, increasing or decreasing their speed. And that's how all of these dirt problems are done. Okay, we're going to solve the equation. Now, sometimes there is no solution because the variable is in the denominator. When the variable is in the denominator, you got to be careful. Okay, so because there's some things that are just not going to be in the domain. That just you're not allowed to plug in for the variable. For example, because the denominator cannot be 0. So if I take this guy here and I say, all right, when is w minus 3 equal to 0? Well, that happens when w is 3. So 3, that guy's out of bounds. So if we solve this problem, we get an answer of 3, we have to throw it away. Because when you plug it in, it makes a denominator 0. That basically breaks the equation. What about another equation or another denominator? Solving, I find that -3, out of bounds. What about that first one? So add 9 and then take the square root and I get positive and -3. They're both out of bounds, but we already kicked them out right there. Okay, so we know that 3 and -3, they are evil in this problem, okay? All right, so how do we actually solve this thing? I mean, yeah, I know I could just say y1 on the calculator, y2, see where they intersect, but let's do it by hand. All right, so first off, you got to factor all your denominators. You got to know what they are. Well, the first denominator factors down to w minus 3, w plus 3. But the other two denominators, they're already linear. They don't factor. So that tells us that our least common denominator is going to be w minus 3, w plus 3. So first thing, or after you figure this stuff out, multiply both sides of the equation by the least common denominator. I think we did that like in the last video or something. Whatever. Okay, so when we do that, when we do that, let's first multiply the first term by that. Well, this denominator is w minus 3w plus 3. So all of that is going to cancel away, all of it. And we're just left with 2w squared. Cool. All right, the second fraction, we multiply that and the w minus 3's cancel, and we are left with 2 times w plus 3. And then the last one, we cancel the w plus 3's and we're left with 3w times w minus 3. Cool. So let's get rid of those parentheses. Let's see, 18w. Okay, parentheses gone. Hopefully I did it correctly. That would be a wonderful surprise. Okay. Combine like terms, and we'll get 20w on the right minus 3. Cool. Right. Now, we continue. Let's get everything on the left side because I like having my a value to be positive. So I'm going to subtract 20w from both sides and then add 3. And I get that. Okie dokie. I don't know if that factors. I guess I'll do quadratic formula. So I'll get w is negative b plus or minus the square root b squared minus 4ac over 2a. All right, so it's going to give me a 20, a 4, a 400, and let's see, 8 times 3 is 24, I guess, sometimes. Okay. And let's see, that's going to be 376, I suppose. Let me pause this, make sure I'm doing it right. Okay, figured out my mistake. Hopefully you saw it already. 3w times w is not 18w. That doesn't even make sense. It's 3w squared. So guess what? I get to redo a lot of things. All right, well, I guess it's not quite that much. All right, so never one to, I did that one wrong too. Never one to restart the video or edit in any way because this is live. This is exciting. All right, so there we go. So now let's combine like terms on the right side. So 2w squared. We're gonna, there's not a lot of like terms here. We've got 2w minus 9w is negative 7w. Okay. And then, okay, so I'm going to subtract 2w from both sides. So I just get 1w minus 7w, or w squared. I wrote it correctly. Okay, I get that. All right, let's do that cool line again. Sorry about all that. Okay, so this one does factor. So it factors down to w, let's see, minus 1, w minus 6, I think. Yes. So when I set that factor equal to 0, I get 1. And this little piggy right here gives me 6. And I already double checked. That is the correct answer. And notice neither of those answers coincides with 3 or negative 3. So we're good. Okay. Everything's hunky-dory. And that's how you do it. So you first have to make sure your denominators are factored to determine what, hang on, let me do a different color. That'll be cool. Make sure the denominators are factored so that you can know what the LCD is, so that you can multiply both sides of the equation by the LCD. That will get rid of the fractions like we have right here, no fractions. And then get everything on one side and then use one of the techniques we've learned, for they are legion. They are a number, not a few. Okay, on this one, now we have a square root in the equation. We have a radical equation. That's rad, dude. Okay, so first off, you have to make sure that the radical expression is already by itself, or make sure it's by itself. In this one, that already is the case. I believe that's the case on all of these. Make sure it's all by itself. Once that's done, you got to square both sides. Now, the wrong way is to leave out the parentheses. And remember, this is x minus 4 times x minus 4. So you got to multiply it out the long way. Get x squared minus 8x plus 16. Okay, now the right side, that's easy. The square root and the square, they cancel with each other. Now let's get everything on one side. I'll subtract, or I'll add 3x to both sides. And I'll subtract 40. Okay. And then I can do quadratic formula, completing the square, solve it on the graph, tinker with the table on the calculator, or maybe it'll factor. It turns out it does. Okay. And I get x equals 8 and negative 3. Now, this problem does not have a variable in a denominator, so I don't have to worry about that. But it does have the other potential problem. It has a variable inside of a square root in the original problem. Therefore, I gotta make sure that my answers are legitimate. Now, whatever, we only do square root of positives and zero. So whatever is inside the square root must be at least 0. Whatever's inside the square root must be at least 0. We know that. I'm just writing it down, that's all. But it's what you already know. So I'll subtract 40 from both sides. And then I'll divide by negative 3, which flips the inequality around. Okay. Now 40 thirds, let's see what that's like, 13 and a third. Okay, so this says, hey, if what's inside the square root is going to be greater than or equal to 0 and be something that's okay, well, x has to be at least, or has to be smaller, has to be less than or equal to 13 and a third. Well, guess what? These guys are both less than 13 and a third. Cool. So they should both work out. Okay. Wouldn't be a bad idea to to plug them in and test that out for sure. In fact, you know what? Why don't we just do that? Yeah, what the heck? I'm feeling kind of wild and crazy. So let's just do that real quick right now on the calculator. So I'm going to go to y equals, clear out my old stuff. It's old data. Pay it no mind. Okay, so x minus 4, that's going to be the left side of the equation. And the right side was square root of 40 minus 3x. Okay. And all right, cool. Now let's go to the table and let's check out 8 and negative 3. What's going on at 8 and negative 3? And I really couldn't tell you. Well, when x is negative 3, does it make the left and right sides match? No, it doesn't. It's really close, but not quite. So even though negative 3 is in this domain, is in the domain of being a number less than or equal to 13 1/3, I still got to check. All right. So, negative 3, you're out. You're not one of our numbers. You're not one of us. We don't like you anymore. Okay, so what about 8? I don't know. Let's find out. Usually one of them works. Yeah, okay. It makes the left side and the right side of the equation match. So 8 is a keeper. He's a keeper. Isn't that something they talked about in that third Toy Story movie? Yeah, that was good. So 8 is our total answer. That's it. Okay, negative 3 is what we call, I forget what they call it. Anyway, it's an answer that pops out. You did everything correctly, but it doesn't really work. Okay, I forget the name of it. I usually know it. So on these radical equation problems, you have got to check your work. Okay. Now, if something is not in that domain, it's automatically out of bounds, but you still got to check your work. Okay. Got to check it. Okay. So now we get to do more word problems. What more could a guy ask for, right? All right. So, if an object is dropped from a height of h meters, hits the ground after t seconds. All right, so h, that's the height it's dropped from, and t tells us how long it's going to take to hit the ground. All right, so it says, suppose that an object is dropped from a building that's 422.38 meters tall. Aha, that is meters, okay, which means it's height, which means we're going to plug it in for h, for height, okay? So let's go do it. In fact, you know what? I'm just going to do it on my calculator. So everybody, you can just deal with it. All right. So I'm going to go square root of the h, which is 422.38, divided by that other number, 4.9. And our answer, let's see, rounded to the nearest tenth is going to be 9.3 seconds. 9.3 seconds. That's how we do it. Not a real big deal. Now this problem, the advanced version, is not that advanced, but that's what they call it. Okay, so a pendulum is L meters long. So L is length measured in meters. Wow, this is like Big Ben or something. That's a long pendulum. Okay, the time t in seconds that it takes to swing back and forth once. So the pendulum starts up here and goes zoom, zoom. How long it takes to go back and forth, one whole revolution, is given by this cool equation right here, where L is the length and t is the time measured in seconds. Because the longer a pendulum is, well, the more time it takes. That's just physics. So suppose the pendulum takes 6.16 seconds. Aha, so 6.16, that's time. So that's going to get plugged in for time. All right, so we're going to get 6.16 equals 2 times square root of L. And the question is, how long is L? So I will divide both sides by 2, get 3.08 is square root of L. And then square, wait a minute, I want to change my color because it's fun. Okay, so I'll square both sides. Okay, those guys cancel, the square root and the square. And we just need 3.08 squared. And let's see, 3.08 squared. 9.5 seconds. Or no, I'm sorry. No, we were solving for L. So 9.5 meters. L is a meter, measured in meters. So 9.5 meters. Wow. That's fairly long, okay, because there's about 39 inches to the meter. So if I multiply, let's see, so 9 meters, what is that like? Yeah, so if I multiply that by about 39 inches, this is like a 369-inch, 370-inch pendulum. If I divide that by 12, I see that it's about 31 foot. 31 feet, yeah, so this is like Big Ben. This is a big clock, or at least a big pendulum. It doesn't have to be on a clock, I guess.